Assalamu alaikum, dear students. This is the 9th lecture of numerical analysis. This lecture is related to the natural cubic splines using system of equations. In the previous lecture, I talked about the basic definition of the cubic splines, and we considered the example. Now in this case, of course, the system has been obtained using the conditions of the basic definition which you discussed before. This time let's see that how, because in that case you saw that if you're having n minus 1 n number of splines and n plus 1 number of data points, then the number of unknowns to determine were 4n. But this lecture will reduce. It will focus just on the computation of the coefficients of the x minus xj whole square. And then rest bi's and di's can be computed from the ci's which we discussed last time. A's, these are the constants. Bi's were the coefficients of x minus xi. Ci were the coefficients of x minus xi whole square, and di were the coefficients of x minus xi whole cube. So remember, we will be focusing only on the coefficient of x square. So let's see that how it works. The target is to construct the cubic splines S of x, which you already know. I will be presenting them over here. These are the cubic splines when you're having data points x0 f of x0, x1 f of x1, and finally xn f of xn. This is the partition of the interval, and we assume that this function, which we are replacing by cubic splines, this will be defined in the interval from a to b. What we did here, we did the partition, we divided this interval into n number of sub-intervals, and you can see that there are n plus 1 number of points. So this is previously, these are the splines which we are defining. Means that S0 is the spline between x0 and x1. Similarly, S1 will be the spline between x1 f of x1 and x2 f of x2, and so on. Sn minus 1 will be the spline between the points xn minus 1 f of xn minus 1 and xn f of xn, which is the related to the last lecture which we did. If you use the conditions of the definition, and if you remember, there were 6 conditions which we were using, and the conditions were about the continuity of the spline, continuity of the derivative of the spline, second order derivative of the spline, and finally the conditions at the boundary points. So here are some equations that has been derived. I'm not going for their derivation, but remember the conditions which we discussed last time, they have been used here. If you look at this plan, when I replace x by xj, so this portion becomes 0, and we left with aj, which is equal to sj at xj, which you can see over here. And since this spline passes through the point xj f of xj and xj plus 1 f of xj plus 1, so it will satisfy these points. Means that when I replace x by xj in this spline, so the final value will be equal to f of xj, and that's the condition which we have written over here. And if you remember, this was first condition in the definition of the cubic splines. This is an extra term which was not there in the previous case. Remember, we are defining a spline between two consecutive points, initial point and final point. If they are known, then we can find out the complete spline. But at the moment, just imagine that we are defining a spline at xn, which is the final point. So that will be starting from xn, f of xn, up to another point. But remember, we don't have that point. And that's the reason if I define this kind of spline, this spline will be passing through xn, f of xn. And the other point is not known. So if you look at it, we have defined this at the initial point. So when I replace x by xn, I should get f of xn. So when I replace x by xn, so you can see that this portion becomes 0. This portion becomes 0 and we are getting an. An will be, since this spline passes through xn, f of xn, so when we replace x by xn, so we are getting f of x, and that is the known quantity. So this an can be obtained from this formula. But remember, xn is the common point for this spline and Sn minus 1, which we discussed before. Again, I am telling you, we are not in the position to find out all values of A and B and C and Dn. But we can find out some of the values. And that's the reason we are using this spline for a particular purpose. I need An in this system. That's the reason I talked about this spline. But remember, our target is not the calculation of this spline completely, but we will be using some of its portion. If I take its derivative, it will become Bn plus 2Cn x minus xn and 3dn x minus xn square. And again, you can see that when you replace x by xn, the multiples of c and dn become 0, and we can find out bn because of the continuity of the two consecutive splines. And the two consecutive splines are Sn minus 1 and Sn. So if I say Sn minus 1 and Sn coincide at xn, so Sn minus 1 is the spline which is completely known. But when I substitute the value and its derivative, Bn can be computed. And similarly, if I take the second order derivative, that will become 2Cn plus 6dn x minus xn raised to the power 1. And when I replace x by xn, so again the multiple of dn becomes 0, and Cn can be linked with Sn minus 1 double order derivative at xn. Since Sn minus 1 will be the spline which is completely known, so I can find out the value of Cn using Sn minus 1 because of the condition of continuity. Lekin further I can't go, because when I take the next order derivative, I need dn ds not computable, and that's the reason I'm telling you that I am using this spline for a particular purpose. But remember, this is not computable completely. We can find out an, we can find out bn, we can find out cn, but we can't find out dn. In this system, I need an and cn. I don't need bn, and I don't have any interest in the computation of bn, because this is not the targeted spline. And secondly, it's not computable. It's not possible for us. So that's why I need an and cn in this system. You will see later on. So I'm just defining this for a particular purpose. What is hn? Hj I will be using. This is the step size between xj and xj plus 1. Remember what I am doing here, I am saying that it's not necessary that the data will be equally spaced. That's the reason we use subscript for hj. h0 is equal to x1 minus x0. h1 is equal to x2 minus x1. h2 is equal to x3 minus x2, and so on. hn minus 1 is equal to xn minus xn minus 1, and that's the reason I'm going up to n minus 1. This is straightforward. So in other words, I can say that whenever you are calculating the cubic splines, it's not necessary that the data will be equally spaced, and which is straightforward from this step size. When I use the conditions which we discussed in the last lecture, we can end up with the value of bj by this formula. Again, I am telling you, I'm not deriving it. It has been derived in your book. So you can, if you are interested, you can go for that. But my target is how to apply these equations. Remember, these equations are coming from the conditions of the definition which we discussed last time. Similarly, the value of dj can be expressed in this form. Again, it can be found over there. This is the main equation. And if you look at this equation, bj, it depends upon aj, which are coming from here. I don't have any problem. Cj, we have to find out this. dj depends upon cj. So if you look at it is independent of any other constant, aj. bj and dj depends upon, because these are known quantities, it depends upon ci's only. So if I know about the values of ci's, I can find out the values of bi's and di's. We don't have a problem. But if you look at this equation, this is the main equation. Again, it's coming from the conditions which you studied before. If you look at this equation, there is a hi's, hj's. They are known quantities coming from the data. We don't have the problem with it. Aj's, they are known quantity which are coming from the data again. The only thing is ci's. If we compute ci's from this system, how many equations are here? J is starting from 1 up to n minus 1. Why I'm starting from 0, I will explain it right now. But if you look at this one, there are n minus 1 number of equations. J is equal to 1, 2, 3 up to n minus 1. It's clear from here. Now let's see that why I was going for an. Look at this equation. When I replace j by 0, this will give me a1 and a0. a0 is coming from here. We don't have problem with it. a0 is using here. We don't have the problem. We can compute that. When j is equal to 1, this will be a0. a0 we can get from here. But when I substitute j is equal to n minus 1, so look at this one. when j is equal to n minus 1, I need an. And that is the reason I used en. The computation of en is straightforward. That's the reason I just for a particular purpose I defined this one. But I'm not computing this completely. So this en is using here. And this en is using here. That was the reason, because j is equal to n minus 1, so you need an. That was the reason I introduced an. Why I'm writing en? It's straightforward coming from here, and f of xn is a known quantity. That's the y component of xn in your data. Similarly, if I substitute j is equal to 0, c naught, yes, I need it over here, c naught. But if I substitute j is equal to n minus 1, you are getting cn. And remember, in these splines, we don't need cn. But we need cn in the computation of bn minus 1. That is the reason I introduced this spline for a while. Similarly, it's using over here. And similarly, if you look at it in this system, cn is there. So I need cn, and I told you I can find out some portion of this spline, but remember, can't completely. Now let's focus on this equation. There are n minus 1 number of equations. Unknowns are, when n is equal to 1, you need c naught. So of course, the starting value is c naught, and which is clear from this spline also. When j is equal to 0, I need c naught. Similarly, if I proceed, j is equal to n minus 1, cn. So unknowns are c naught, c1, c2, c3 up to cn. And I need c naught, c1, c2 up to cn minus 1 only. But since cn is using here and it is using here, that is the reason we are computing cn here. C naught, c1, c2 up to cn, there are n plus 1 number of unknowns. But if you look at this system, there are n minus 1 number of equations. We need 2 more equations. And from where these 2 more equations will be coming? They will be coming from the boundary conditions. So at the moment I am talking about the natural splines, and you can see that natural splines are given by these 2 conditions. Look at this one. I have taken its second order derivative. So this is straightforward. Take first order derivative and second order derivative. Finally, we are getting this. And now if you replace in this first condition x by x naught, so this portion will become 0, and you will get 2c naught is equal to 0, which gives you c naught is equal to 0. So I got 1 equation. N minus 1 number equation plus 1 equation, so we got n equations. But remember, unknowns are n plus 1. So let's come to the second condition. Second order derivative of the last spline at the end point is equal to 0. This is straightforward, you already know it. But let's see here. This is the condition of continuity of the second order derivative for the cubic splines. And you can see Sn minus 1 and Sn, these are 2 consecutive splines. And Xn will be, because Sn minus 1 lies on the left hand side and Sn lies on the right hand side. So if this is the spline, so this condition will satisfy. Now at the moment, forget about this one. This is known. because Sn minus 1 spline is completely known. So we can deal with it. But when I replace x by xn in this spline, you can see that this portion becomes 0 and you left with 2cn only, which you can see which appears here. No, now when I ignore this portion, so 2cn can be expressed in this form also. So in terms of Sn minus 1, I can find out the value of Cn, which is the value required here and which is the value required there. But since this is equal to 0, so in other words, I can say that 2Cn is equal to 0. And 2Cn is equal to means that Cn is equal to 0. This is another equation. So n minus 1 number of equations plus 1 n number of equations plus 1 n plus 1 number of equations. So if I use this equation, this one and this one, so I completed my system. So previously you saw that we were looking for 4n number of unknowns and 4n number of equations were required. But in this case, the problem has been reduced. Instead of solving 4n by 4n system, we are solving only n plus 1 by n plus 1. And that automatically that will reduce your calculation. There are two ways. Either use C naught is equal to 0 and Cn is equal to 0 in all these equations, and then you will have n minus 1 number of equations and n minus 1 number of unknowns. So you can deal in that way also. But remember, I'm counting n minus 1 equation plus this equation to go for the complete system. So let's see. This is our system now. C naught is equal to 0. And this is the main equation, j starting from 1 up to n minus 1. It means that n minus number of equations, this expression represents n minus 1 number of equations, and this is another equation. So let's write this in the matrix form. Let's start from here. Coefficient matrix. I'm constructing coefficient matrix first. Coefficient matrix means that I'm dealing with this portion. Now, this column I have fixed for the coefficients of C naught, for coefficients of C1, for coefficients of C2, for coefficients of C3, for coefficients of C4, and for coefficients of Cn. So let's see. In the first equation, you can see that I can write this equation 1 multiplied by C naught is equal to 0. So the coefficient of C naught is 1. And that's the reason I have used 1 here. And rest of Ci's are missing in this equation. So their coefficients are 0 totally. Come to this equation when j is equal to 1. When j is equal to 1, so you are getting h naught multiplied by C naught. So the coefficient of C naught is h naught plus 2 into h naught plus h1 multiplied by C1. The coefficient of C1 is 2 into h naught plus h1, which you can see over here, plus h1 C2. The coefficient of C2 is h1, and we don't have more Ci's. That's the reason you can see that the rest of the coefficients are, means that the coefficients of C3, C4, C4 up to Cn, they are 0. So that's the reason you can see 0 there. Right hand side, I will discuss this after this coefficient matrix. When j is equal to 2, j is equal to 2. So I am writing this equation in the third row. J is equal to 2. So this is h1 multiplied by C1. So you can see the coefficient of C1 is h1. J is equal to 2, coefficient of C2 is equal to 2 into H1 plus H2, which you can see here that the coefficient of C2 is 2 multiplied by H1 plus H2. And H2 multiplied by C3, the coefficient of C3 is H2, which you can see over here. And the rest of the coefficients are zeros. Similarly, for J is equal to 3, J is equal to 3, you are getting H2 C2, coefficient of C2 is H2. C3, coefficient of C3 is 2 multiplied by H2 plus H3, which you can see over here. And H3 C4, the coefficient C4 is H3, which you can see over here. And we don't have more Ci's, so rest of the coefficients are zeros, which you can see over here. I will continue this until J is equal to n minus 1. J is equal to n minus 1. So this will become Cn minus 2. This will become Hn minus 2. The coefficient of Cn minus 2 is Hn minus 2, which you can see over here. And similarly, this will become Cn minus 1. The coefficient of Cn minus 1 is 2 multiplied by Hn minus 2 plus Hn minus 1. And you can see this coefficient over here. And this will become Cn. Cn coefficient is Hn minus 1, which you can see over there. So you can see now these are the rows coming from this equation. And finally, if you look at it, it can be written as 0C0 plus 0C1 plus 0C2 plus so on, plus 0Cn minus 1 plus 1 into Cn minus 1. So the coefficient of Cn is 1, and that's the reason you can see 1 is there. So you can see that these three lines gives you this n plus 1 by n plus 1 coefficient matrix. What are the unknowns and BI's? Unknowns, I told you, C0, C1, C2 up to Cn minus 1, and finally Cn. So these are the unknowns to be determined. Remember, they are already C0 and Cn are already known. Doesn't matter if you are excluding them, you can do it. There is no any problem. B, coefficient for the first equation, right hand side is equal to 0. You can see 0 here. When J is equal to 1, this will become 3 divided by H1, which is there, multiplied by A2 minus A1, which is there, minus 3 divided by H0, which is there, multiplied by A1 minus A0, which is there. And when J, this correspond to the first row, and this correspond to the second row, which correspond to the equation coming from here. When J is equal to 2, so that give you third row. So there will be third row also. So when we substitute 3 divided by, this will become H2, A3 minus A2, which is there, minus 3 divided by, this will become H1. This is H1. Three divided by H1 multiplied by A2 minus A1. So you can see it corresponds to the third row. When J is equal to 3, this will become 3 divided by H3, which is there. This will become A4 minus A3, which is there, minus 3 divided by H2. This will be H2. Sorry, I did this mistake. A lot of calculation is there, so that's the reason sometimes we can get some error. So this is 2. And finally, when I continue, j is equal to n minus 1. So this will be 3 divided by hn minus 1, en minus 1, minus 3 divided by hn minus 2, multiply by en minus 1 minus an minus 2, which you can see over here. So now you are having these three lines have been reduced to ex is equal to b, which you can see in this form. This is n plus 1 by n plus 1 system. And I told you in the last lecture that cubic splines have been defined in such a way that they must have a unique solution for these unknowns. So E inverse is possible, that A will be non-singular matrix. You can find out it and then multiply by B, you will find out X. So what is X? X is the column matrix of Ci's. Once the values of Ci's are known, you can find out the values of Bi's and Di's, and that will complete your system there. So I will be going for an example. I got this system, Ci values we will compute, and in previous slide I showed you that the values of Bi's and Di's can be computed from Ci's. Now the target was to find out the values of Aj, Bj, Cj, Dj. The values of Cj you computed from the system, Aj from the data, Bj and Dj can be computed from the equation which I showed you before. Let's use this idea to construct a natural cubic spline for the data given in this table. Now look at this table. How many points do we have? X0, 1, 2, 3, 4. 3 splines we can construct. And we number this is X0, X1, X2, X3. So when I say X3, the value of n is equal to 3 in your problem. Let's see that how we can. So this is the normal routine. This is the normal equation for the cubic splines. But remember, I told you the value of n is equal to 2. So value starting from 0 reaching up to n minus 1, 3 minus 1 is 2. So you're having 3 splines in this case. For the first spline, which lies between the first 2 points, we represent it by S0 and S0. J by 0 in the equation, and xj by minus 1. So minus and minus will become plus. So that's the reason you can see plus here. X minus minus 1. So that will become x plus 1. And that's the square component. That's the cube component. This is the first spline defined between these 2 points. Now let's define the spline between minus 5 and 0. Minus 5 and 0, the spline is defined by the value of xj, that will be x1, in this case is minus 5. So this is minus 5. X minus minus 5, minus 0.5 is x plus 0.5. This is x plus 0.5 square. This is x plus 0.5 whole cube. And the value of j is equal to 1. Now let's define another spline between 0 and 0.5 in this interval that is given by this spline. So A2, the value of j is 2. This corresponds to j is equal to 2. And xj is equal to 0. That's the initial point of your interval. These are the 3 splines we have to find out. And you saw in the previous case that we are having 12 unknowns and 12 equations were required. But this time I need the value of n is equal to 3. So I need just four unknowns, C0, C1, C2 and C3. From where C3 will be coming? If I define a spline between 0.5 and the point which is not known. So I can say that that will be S3, and when that is S3, so x minus 0.5. X minus 0.5 square, x minus 0.5 cube, and the value of j will be equal to 3. We don't need that. But since we need its value, that's the reason we will be defining. We just imagine that we are defining and using for a particular purpose, and then we will throw that into the dustbin. The value of n is equal to 2. Xj was equal to xj plus 1 minus xj in the last case. So if you look at this data, the step size is the same, so h1, h2 and h0, they are the same, and this minus this, this minus this, this minus this gives you 0.5. so the data we are using here is equally spaced data. Aj is equal to f of xj. I just discussed the equations that these were coming from the condition, and this is the spline which we define and then dispose its spline. That's the reason I'm saying j starting from 0 reaches up to 3. So f of x0, f of x1, f of x2, f of x3. So f of x3 is known, and f of x3 is equal to a3, which we need for our calculation. That's the reason I said that j starting from 0 reaches up to 3. It's coming from there, which I explained in the previous slide. When I use them, x is equal to minus 1, so this portion will become 0. A0 is equal to f of x0, which is given by this quantity, and you can see that's the value of A0. When x is equal to minus 5, so this portion will become 0. We are getting A1, and when we are getting A1 is equal to S1 of minus 0.5, which is equal to f of minus 0.5, and f of minus 0.5 is this value. That's the reason I'm writing A1. Similarly, A2, replace x by 0, this 0, in this equation all the terms will become 0. You will left with A2. A2 is equal to S2 of 0, and S2 of 0 according to the definition is f of 0, and f of 0 is given by this quantity. That's the reason I'm writing A2 is equal to this quantity. Similarly, A3 is equal to f of x3. x3 is 0.5, so A3 is equal to f of 0.5, which you can see over here, which I will be using in the computation of CIs, BIs and DIs. So you can see that these are straightforward, and you already know that how we can find out it's coming from the data. So we don't have problem with this one. Let's go further. This was the system which I discussed before, that we got the coefficient. This is the coefficient matrix of CIs, and this was the right side. Now in this example, the value of n is equal to 3. I told you there are 4 points the value of n is equal to 3, because x0, x1, x2 and x3, the value of n is equal to 3. So how you will reduce this coefficient matrix? Now see that for natural spline, this is coming from S0 at x0 is equal to 0, a double order derivative, and Sn minus 1 double order derivative. But remember, this is related to CIs, so C0 was equal to 0 coming from there, and Cn was equal to 0, it's coming from there. That's the reason you can see 0 on the top and at the bottom. So it is there. But n is equal to 3. So let's see that from where you are starting. You are reaching up to C0, C1, C2 and C3. Coefficients of C0, coefficient of C1, coefficient of C2 and coefficient of C3. You have to be careful. I'll be focusing on this one. What should be the last term in my matrix? It's okay. This is for the first one. This is for the second one. This is for the third one. So let's see that how it works. N is equal to 3. N is equal to 3. It gives you H2. See that where is the last H2? It's coming there. So it means that this is your matrix for this particular problem plus the last row. Last value is H2. This will be H2, H1 plus H2, which is there, and this will be H2. So H2, 2 into H2 plus H3 and H2, that will be your last row. And you can see that last row is there. So it means that the first 3 rows will be coming from there. And you can see the first 3 rows over there. The last row. Just under H2 is 1. Just under H2 is 1, because this will be Cn. So this time your C3 is equal to 0. And for C3, these are the coefficients of C0, C1, C2, C3. That's the reason I'm writing it over here, because C3 was equal to 0. So you can see, if you look at this system, this is tridiagonal matrix. And straightforward, it's straightforward to understand. So you can see this is your coefficient matrix. This is C0, C1, C2, and C3. C0, C1, C2, C3. There will be C0, and we don't have this one. C0, C1, C2, and C3. These are the unknowns to be determined. Now let's come to this one. The value of n is equal to 3. What will be the last? Look at this one. N is equal to 3. 3 divided by H2. You can see this is the one. This will be A3 minus A2. That is the one. Minus 3 divided by H1. So remember, this was the mistake. I copied it from there. So this was your H1 and this was your H2. But remember, we are going up to H1 only, because this will be H multiply H subscript 3. This will be H1. So you are having just that one case. We don't have this. This is H1, and we don't have this one. This is H2. But remember, I don't need this line. I don't need this line. I'm just using the data up to this portion, A2 minus A1. So it means that we are having the first 3 rows, which you can see over here, and the last row, which is coming from C3 is equal to 0. So instead of solving for n by 4n, now you are solving 4 by 4 matrix, and it's very easy to solve it. This is the matrix which I copied from there. Coefficient matrix. Again, this is C0, C1, C2, and C3. So again, this is the, I told you that this is the mistake which we have. So you can do the correction. There will be C0, and we don't have Cn. Let's see that the value of H0, H1 and H2 were the same if you look before. C0 is equal to 0, C3 is equal to 0, we got from the conditions. When I substitute the values, this will be 0.5. 0.5 plus 0.5 is 1, 1 multiplied by 2 is 2, and this is 0.5. This is 0, 0.5, 2, 0.5, which you can see over there, and this is the last row. So you got this coefficient matrix. C0, C1, C2, and C3. These are the unknowns to be determined. B. Substitute the values of AI's and HI's in this matrix. You are getting this matrix B, which is known quantity. Now, X is equal to B, X is equal to A inverse B. You can find out. Now, in the last case, some of the students were asking that this is very lengthy. But now you can see that this is very short and you can find out. You can do it manually. You don't need the programming for it. But it's up to you. I'm not stopping you because if you have a huge system, so you can do the programming. And when we solve X is equal to A inverse B, this is the solution. In other words, the value of C0 is 0. The value of C1 is 0.0985, the value of C2 is 0.1409, and the value of C3 was equal to 0, which you got from the conditions. These values are known. AI's are known. Let's come to this one. This was the formula which I gave you for Bj. So when J is equal to 0, you are getting B0. 1 over H0, A1 minus A0 minus H0 divided by 3, 2C0 plus C1, and Ci's are known from here. Ai's we discussed before, and when you substitute, you are getting the value of B0. Similarly, J is equal to 1, so this is 1 over H1, A2 minus A1 minus H1 divided by 3, 2C1 plus C2, and the value of C1 is there, the value of C2 is there, A1 and A2, H1, they are known quantities. You can find out these values. And similarly, when J is equal to 2, 1 over H2, again there is, this is H2. This is H2. And of course, this will be, sorry, this is H2 or J is equal to 2. So this will be, again, this will be 2 hours. So this will be, that will be your 2 hours. Now C3, C4. I did this mistake. This is 3. And this is 2. The values of A2, A3, C3, this is C2, and this is C3. All these values are known, and when you substitute the values, you are getting the corresponding value of B2. So you are having 3 spline, B0, B1, B2 are required, and you computed them using this formula. The last thing remains is dj. This was the formula for dj. Substitute j is equal to 0. You are getting 1 divided by 3h0, c1 minus c0, c0 is known, c1 is known. You got the value of d0, d1, 1 over 3h1, this is c2 minus c1, c1 is known, c2 is known, h1 is 0.5. You can get the value of d1. J is equal to 2, 1 over 3h2, this will be c3 minus c2, C2, C3 are known, H2 is known, so you can find out. So you can see in this case, you computed the values of AIs, you computed the values of BIs, you computed the values of CIs, and you computed values of DIs. This was your spline. All these unknowns are known now. We computed that before. A0, A1, A2, C0, C1, C2, B0, B1, B2. You can see here I dropped A3, I dropped C3, I didn't compute it B3. These are the values I known. So I used the extra spline which I defined and then dropped that one and completed our calculation. When you substitute the values of AIs, BIs, CIs and DIs in these splines, you are getting the splines given by this quantity. I just went up to 4 decimal places in this calculation. Otherwise, you can go for the complete number. So you computed this is the value of A0. This is the value of A1. This is the value of A2. This is the value of B0, which is coming from there. The value of B1 is here. The value of B2 is there. And similarly, C0 is 0, which is missing here. C0 is 0 now. C1 is there. C2 is there. And similarly, D0 is there. This is the value of D1 and this is the value of D2. And it completes your construction of the natural splines. For example, someone asks you that you replace your data by the spline, but find out the area bounded by your data points. So what you will do, you will do the integration from -1 to 0.5. F of x dx is equal to, because f of x has been approximated by your spline. But remember, there were 3 splines. S0 defined between -1 minus 0.5, S1 between -0.5 and 0, and S2 between 0 and 0.5. And that's the reason I used the property of integration and splitted them accordingly. When you compute this one, integration from -1 to -0.5 S0, this is the value of S0. You can do the integration, and integration is given by this quantity multiplied by x, this quantity multiplied by x plus 1 whole square divided by 2, you can see it over there, plus this quantity multiplied by x plus 1 whole 4 divided by 4, which you can see over here. This is the upper limit and this is the lower limit. Upper limit minus the lower limit, upper limit minus the lower limit. So what you have to do, replace x by -0.5 minus, replace x by -1. You are getting this value. Similarly, replace x by -0.5 minus, replace x by -1. You are getting this value. And do the calculation. Definitely you have to do the calculation. Replace x by -0.5 minus, replace x by -1. You are getting this value, and if you add all these values, this is the value of S0 of x. So the area which is between x is equal to -1, x is equal to -0.5 under S0 and above the horizontal axis. Similarly, if you go for calculation of S1, this calculation, so the value of S1, which is coming from the last slide, and if you do the integration in similar fashion, this quantity multiplied by x, this multiplied by x plus 0.5 whole square divided by 2, plus this multiplied by x plus 0.5 whole cube divided by 3, plus this quantity multiplied by x plus 0.5 whole raised to power 4 divided by 4. Lower limit, upper limit, lower limit, upper limit, lower limit, upper limit, lower limit and upper limit. And now substitute the upper limit minus the lower limit. Do the simplification. this number multiply by, substitute x is equal to 0 minus x is equal to minus 0.5. You are getting this value. Replace x by 0 minus x by minus 0.5. You are getting this third value. And replace x by 0 minus x by minus 0.5. You are getting this value. And if you do the addition, this is the final value. So you can see that between minus 0.5, x is equal to minus 0.5 and x is equal to 0 under the curve S1 of x. The area is given by this expression. Similarly, let's find out the last one. Integration from 0 to 0.5 S2 of x. This is the value of S2 of x. And if you do the integration is straightforward. This multiply by s, x squared divided by 2, x cubed divided by 3, and x raised to the power 4 divided by 4. And again, upper limit, lower limit, you are getting, this is the value of the third integration. Now, overall integration, 8, the 3 integration you got, and when you add them, this is the final answer. So it means that the function, the data you have for a function f, you replace that by s and then computed area under the curve. And if you look at the graph, this is the graph of s. So the graph of S1, hold on the figure, the graph of S2, the graph of S3. So S1 is between minus 1, minus 0.5. This is the graph of S1. S0. S1 is between minus 0.5 and 0. So this is the graph for S1 and this is the graph for S2. When you look at the graph, this is a smooth and continuous curve, and this integration means that you are getting area of this region. So you saw that we have data points, we replace the data points by a smooth and continuous curve and then computed the area under that curve. So this is the area which is bounded by the data points you have. And you can study any point in this curve you like. I just give you a simple example that how you can do the integration. You can play with it, whatever you like. Let us consider another example. This example I have taken from your book so that it become clear to you. Very straightforward. Spline is given to you, natural spline. So of course, when there is the term natural spline, it means that at the boundary second order derivative of the spline is equal to 0. Remember, this time the splines are given to you. But if you look at it, the splines are not complete. B, D, B, and D, these are unknown quantities. You have to find out these values. Not necessarily their points will be given to you, like these are the data points. x0, f of x0. Here S1 has been used, so this will be x1 f of x1, this will be x2 f of x2, this will be x3 f of x3. So S1 is the spline between these 2 points and S2 is the spline between these 2 points. The target is to find out the value of capital B, capital D, small b and small d. You have to think yourself, okay, how I can find out. It has not been asked from you to construct the complete spline. Some portion has been computed. And similarly, if you look at the system which we discuss right now, again, we don't need that because some portion is known. So let's think ourselves, okay, how I can find out the solution. I told you that these 2 splines will be continuous at the common point. So you can see common point is 2. Their derivatives will be, first order derivative will be continuous, second order derivative will be continuous. One point we have to look at it. In the first spline, The splines which we were defining, you were saying 1 is less or equal to x less or equal to 2. But remember, 2 is excluded in this case. And 2 is included over here. This portion is also included. And that's the reason I'm saying it should be continuous. Continuous, we say that left hand limit when x approaches minus 2, a right hand limit when x approaches plus 2 should be equal to the exact value. Exact value you can get from here because S2 of 2 will be equal to f of x2. That's the reason I use x approaches 2 through negative values. It doesn't mean minus 2, remember, as I discussed before. This means through negative values you are approaching towards 2 from left hand side. So you can approach towards 2 very close to 2 but not 2. And similarly in this case you are approaching towards 2 from right hand side. You are taking the large value, greater value, assume you are starting from 3, then 2.5, 2.1, 2.01 and so on. You are approaching towards 2. It means the limit through positive values. And in this case, for example, 1.1, then 1.5, then 1.9, 1.99, 1.999. So you are approaching towards 2. This kind of values we are saying that we are approaching towards 2 from left hand side. Left hand, for continuity, left hand limit should be equal to the right hand limit should be equal to the exact value. That I use their definition. But look at S1. I don't have problem when I replace, and you know that in case of limits, when you are replacing limiting value x by a, and it doesn't create any problem for you. 0 by 0, you are infinity by, and you are not getting indeterminate form. The limits are saying that straightforward substitute the value. The value you are getting from here will be approximated value, not exact value. That's why limit is there. And when I substitute, because I have nothing in the denominator, that's the reason I replace x by 2. So this is 1. 2 minus 1 is 1, so b, and 2 minus 1 square, 1 is minus d. You can see is equal to, this portion will become 0 and you are getting 1 only. 1 and 1 will cancel and you are getting b minus d is equal to 0. Let us check the continuity of the derivative. So this is the continuity of the derivative. What is the derivative of this spline? Just take the derivative s1 prime, it will be 0, b minus 3d into x minus 1 square. This is the derivative of s1. The derivative of s2, this will be 0, b minus 3 divided by 2, because 2 has been multiplied with the 3 divided by 2 x minus 2 plus 3d into x minus 2 whole square. Again, I don't have problem when I replace x by 2. So I approximated the approximated value, that is 2. So this will be 2 minus 1 is equal to 1. b minus 3d is equal to, this portion will become 0 and you are getting b. How many unknowns you have? 1, 2, 3, 4. We need 4 equations. This is the first equation. This is the second equation. Let's go further. Let's see the derivative, second continuity, the second order derivative of s1. a2 should be equal to that of second order derivative is 2a2. So you can see, since this is not included, that's the reason I use limits. And when you replace x by, if you look at the second order derivative, so if you take the second order derivative, this will become 0 minus 6d into x minus 1. This derivative will be 0 minus 3 divided by 2 plus 6d into x minus 2 power 1. And again, we having nothing in the denominator, therefore we replace x by 2 minus 6d. This will become 0 minus 3 divided by 2, and you can find out the value of d from here, which comes to be 1 divided by 4. Similarly, I got the value of d from here. Let's find out the value of b from there, because from equation number 1 you can see that b is equal to d. D is 1 by 4. That's the reason b is also equal to 1 divided by 4. We got the value of b, we got the value of d. Substitute the value over here. B is known, D is known. You can find out the value of small b. So from equation number 2, the value of b is minus 1 divided by 1 by 4 minus 3 divided by 4 is minus 2 divided by 4, which is minus 1 by 2. Computed b, capital B, small b and capital D. Small d is remaining. I use the continuity of the spline, its derivative, its second order derivative. So let's go. What we can do for the next equation. Since the splines are natural, these are the conditions. 3 was the endpoint. Second spline at 3 is equal to 0. First spline at 1 is equal to 0. What is the second order derivative? Second order derivative, if you replace x by 1, so automatically this condition is satisfied. So it can't help me in the computation of small d. Now let's use the second one. What you are getting from here. Minus 3 divided by 2, replace x by 3. 3 minus 2 is 1 plus 6d is equal to 0. And it is straightforward to find out the value of d from here, which is 1 divided by 4. So you saw in this case that we computed the missing values. So remember, you have to use your own mind. Different cases I discussed. I use the basic definition, have the problem with the basic definition, then I use the system, and then I took an example. Some portion is known, how you can find out the missing portion. So remember what we did in this case. We use the properties of the splines. But remember, I use the property of the continuity also, which is coming from your calculus. So this is your previous knowledge. And we computed, when we substitute these missing values in the given spline, we will get the complete spline. And again, if you plot your spline between 1 and 2 is 1, and the second spline is 2 between 2 and 3, then you will be getting a smooth and continuous curve. So remember, the splines are you are replacing your data by curve. You can study the curve, you can find out the area, and if some portion is unknown, then you can find out some of the portion, the missing portion, and complete your splines. Thank you very much.